we talked last time about dealing with what we have is non-homogeneous differential equations. So recall that when we say non-homogeneous is you have this piece on the end, this f of t, which is non-zero. And we want to deal with that. How do we handle this? And we talked about saying there were two ideas for handling non-homogeneous problems, and we did one of them last time. And so the one we talked about last time, just as sort of a reminder, was we called it undetermined coefficients, but really you should think of it as undetermined vectors. And so what we have is we say, oh, we recognize the pieces are the kind of pieces that we would normally expect to see coming out of solutions to systems of differential equations. And so, well, what we'll have is we'll have those pieces, those little functions individually pulled apart. Each one of them has a vector, and then we have to figure out the vector. Now, we're going to talk about a second method. And I'm going to tell you right now that if you ever have the choice between undetermined vectors / undetermined coefficients and variation of parameters, it's almost always easier to run through undetermined coefficients. But it's not always an option. So that's why we're talking about today, which is called variation of parameters. And so it starts by saying, e to the at, which we sort of introduced as this way of phi of t, phi inverse of 0. Well, this is sort of a weird way to write this. This is phi of 0 to the negative 1 power. It's actually pretty nice. So remember, we had a different way of thinking about e to the at, namely it's the identity plus t times a plus 1 over 2 factorial t squared over a squared, and so forth and so on. And we say, does it really behave like an exponential function should? Well, as a quick example, let's think about nice properties of the exponential function. What's the derivative of the exponential function? Itself, right? Well, if I have the derivative of, say, e little at, what's the derivative of that? That little a comes down. Well, now we have a big A. Does that still hold true? Well, we can take the derivative over on this side. So if we run through and just convince ourselves of the computation, the derivative of the identity matrix would be what? Zero. Because identity matrix doesn't vary. And when we talk about derivatives, we're asking how much do things vary. So actually, you should think of the matrices are acting like constants here. The matrices aren't the parts that are varying. The matrices, it's the parts with t. Okay, so that goes away. The derivative of t, 1. So we would have an a. Derivative of 1 over 2 factorial t squared. So the 2 comes down, and it cancels with the 2 factorial, so you really have t a squared. How about here? Derivative of 1 over 3 factorial t cubed. The t squared. Okay, but what's the coefficient? Yeah, we can even say 1 over 2 factorial, because you can think of 3 factorial as 3 times 2 times 1. The 3 cancels. And now we have a cubed and dot, dot, dot. We say, oh, look, each one of these has an a. So you pull it out in front. I plus ta plus 1 over 2 factorial t squared a squared. We say, what? That's what we started with the e to the at. So we actually do get a e to the at. So that's pretty cool. And so you can get a couple of things out of that. Now, this gives you several checks, by the way. Let's just convince ourselves of a few things. What would be e to the a times the number 0? Okay, we say 1. But remember, this is a matrix, so what's the equivalent of 1 for a matrix? Identity. So if you have something which you think is an exponential matrix, plug in 0, and if you don't get the identity, it's not an exponential matrix. Okay. Now, imagine that we took the derivative of e to the at, and then, after we took that derivative, then we plugged in 0, what would we get? So remember, this notation means we do an evaluation. So we take our derivative when we plug in t equals 0. So what do you have when you plug in t equals 0? You get a. So this is sort of a double check. If you're like, well, I don't want to rederive everything, can I check my work in a different way to see if I have the right exponential matrix? Well, just take the derivative. Usually that's not too bad. Plug in 0. If you get a, 100% has to be it. If you don't, mistakes were made. Well, let's try another concept here. If I took e to the at and we did the inverse, what do you think that should be? Well, we're not doing the inverse function of this. It's to the negative 1 power. It's like we're taking the inverse of a matrix. What do you think that will be? Yes. Someone has secretly said, oh, look, it's right over here. E to the negative at. So in other words, things work pretty nicely. So, okay, great. Wonderful. So this e to the at, it's got good stuff going for it, other than it can be a little bit annoying to compute. Say, okay, fine. Now, let's suppose that we start with this differential equation, x prime equals ax plus f of t. And even though we're calling this variation parameters, we're going to channel sort of a different vibe. We're going to go back to, I think it was the second week of our class, and say, all right, how did we solve a linear differential equation? Well, we said, all right, what you should do is you have x prime minus ax equals f of t. Okay, so you said, all right, that's sort of the starting point. And then you said, well, we need to do an integrating factor. So you'd integrate negative a, well, that's negative at, and then you put that in the exponential function. So that's e to the minus at. So really this e to the minus at, this is acting as our rho, our integrating factor that we talked about at the beginning of the semester. So we have e to the minus at times x prime minus a e to the minus atx equals e to the minus at f of t. Again, it's just multiplying through by rho. And then we say, aha, this left-hand side is a derivative. So we say, oh, that's really the derivative of e to the minus at times x. We say, well, that's great. How do you get rid of a derivative? You integrate. So you have e to the minus atx is the integral of e to the minus at f of t dt. Now you say, well, I don't want e to the minus atx, I just want x. So how do you get rid of the e to the minus at? Well, we move it to the other side. So how can we move it to the other side? Well, the answer is we would multiply by the inverse of e to the minus at, which would be e to the at. So you're multiplying on both sides by e to the at, because then those cancel in the sense that they become the identity. So we have that x equals e to the at integral e to the minus at f of t dt. Now, two comments. When we integrate here, this part right here is a vector. So what kind of a constant will we get out of it? Well, when you integrate a vector function, you can think of your constant as being a constant vector. Or you can think of it as like I have a constant in the top entry and I have a constant in the next entry. And we'll stop at 2 by 2s, but you have a constant for each one. Now, you have two things that you can do. So if you have all constants 0, okay, I started spelling have, and then I ended spelling all constants equal 0, you have the function xp. So this is the particular solution. If you have arbitrary constants, then what will you have instead of the particular solutions? Well, then what you have is the general solution. All solutions will show up. So it depends on what you're looking for. If you're looking for a particular solution, just say, I assume my constants are 0. If you're looking for the general solution, arbitrary constants, and life is good. Now, that was one comment. My other comment. If you go back to what we did at the second week of class, where you start with our x prime equals ax plus f of t. Nothing bold, just function of x, just a number a, just f as a normal function. Then, the same idea says that x equals e to the little at integral e to the minus at f of t dt. So, in other words, over the course of the last 2 months, we have gone from a lowercase a to an uppercase a. So you can call your family and you say, you remember how excited I was at the beginning of the semester and how I said there was a lowercase a? But now we can do it with an uppercase a. Progress. Where will we be later? So. Well, thank you. I'll be here all semester. So, but all right, good. So anyways, that's the idea. That's the idea. All right. Well, of course, that's the idea. But now we should do some practice. Any questions? Okay. Our first example. Find the general form for solutions to x prime equals 2 minus 1, 5 minus 2x plus 0 secant t. Okay, so before we start, is this a problem that we could do undetermined coefficients on? No. What's the problem? Secant is not one of our nice functions. You have to look at things which are t to a power, e to a exponential function, sines or cosines. If it's not on that list, forget it. Hopeless, hopeless. So we can't do method of undetermined coefficients. So that's good. It's nice that we have options. Say, okay, great. So we know where we're going. We know x equals, we'll write down our formula, e to the at, integral e to the minus at f of t dt. So that's where we're going. Say, all right, what are our pieces? Well, our f of t, 0 secant t, so that's pretty good. And our a, that's just the matrix of these coefficients, 2 minus 1, 5 minus 2. Okay, so given that we have our formula, we have our pieces, what's the first thing we should go about doing? Really, where's our direction going to be? Where are we moving towards? Yeah, in essence, we're probably the first big step in our process is getting e to the at. E to the minus at is essentially a freebie once you have e to the at. You don't even have to think about it. And we'll show you what we mean when we get there. Okay, so we know we're shooting to get e to the at. All right, so if we're shooting for e to the at, what do we do to a at the start? Eigenvalues. Yeah, you always need to start with the eigenvalues. Now, let's hope that these are good eigenvalues. Well, all eigenvalues are good. So we take our determinant a minus lambda I. So that's determinant 2 minus lambda minus 1, 5 minus 2 minus lambda. And, okay, so that's 2 minus lambda minus 2 minus lambda. Subtract 5 times negative 1. Minus 4 Then we have a minus 2 lambda and a plus 2 lambda, so those actually cancel. Plus a lambda squared plus 5, which is lambda squared plus 1, and that has to equal 0. What does that tell us about our eigenvalues? Yeah, complex. This problem just got a little bit more complex. All right. I think I'm supposed to like put the shades on. This problem just got a little bit complex. Okay, good. So, we got our eigenvalues. Now, we have complex numbers. We say in our hearts of hearts, this is good news. Why is it good news? What do we see in here? Secant, that's a trig function. So we'd like to have trig functions being involved. When we have complex roots, especially when there's no real part, it's just pure complex, we say, we're heading towards sines and cosines. And sines and cosines get along well with secant. So that's good. They gave us a nice one. By nice, I mean solvable. Okay, so eigenvalues done. What comes next? Eigenvectors. And when we're doing complex, we only have to do a single eigenvector because we're going to sort of take our single eigenvalue eigenvector pair and produce our two solutions. So we say, okay, lambda equals I. So we have our matrix 2 minus I minus 1, 5 minus 2 minus I. And we have to find something that multiplies. Oops, I did not plan very well. Something to put in. So when we multiply, we get 0, 0. Do we have any such something that works? I think 1, 2 minus I might be the easiest one that I see. So I like to take a row, and I usually look for a row that looks simpler to work with. So the top row looks a little bit easier. And we're putting it kind of in the wrong order. So usually we'd go left, right. Now I'm going like right to left. And then I have to flip the sign on one of them. Okay, so our eigenvector, 1, 2 minus I, but now we break it apart. What's the real part of this eigenvector? 1, 2. And then we're going to add I in the imaginary part. 0 minus 1. Okay, so here is our eigenvector. Okay, good. So our next thing is we're going to form our solution. So we take our eigenvalue, e to the it. We always say that's really cosine t plus I sine of t. And then we're going to have our eigenvector 1, 2 plus I 0 minus 1. And we FOIL and we gather. So we have that our general solution, x equals a, real times real, cosine t, 1, 2, and then imaginary times imaginary, minus sine of t, 0 minus 1. So the minus because of the I squared. Plus the second part, which is the imaginary pieces, cosine t, 0 minus 1, and sine of t, 1, 2. Okay, so those are our two parts, our two functions. All right, so, I shouldn't use a here. All right, let me change it to this kind of an a. There we go, a and b. So, do we have e to the at yet? And if we don't have e to the at, how do we get there? What have we found? Let's make sure we know what we found. What have we found? We found the general solution. Now, when we're looking for e to the at, how do you go about finding that? Well, unless you get lucky and have repeated eigenvalues, which is, that's a great case, the way we generally do it is we take our general solution and make a fundamental matrix, and then we do a quick correction. So let's start by throwing our two solutions here in as our columns, cosine t, 2 cosine t plus sine t, sine t minus cosine t plus 2 sine t. Now it's possible that this is the right matrix. It's not, but sometimes you get lucky. So what else do we need? We need the inverse at 0. So we plug in 0. Everywhere you see a cosine goes to 1. Everywhere you see a sine goes to 0. So you get 1, 0, 2, minus 1. And you probably are thinking like, whoa, those look familiar. We've seen these before. Where have you seen those before? What do you think? Coincidence? No. No. Not a coincidence. All right, and we're taking the inverse of that. Okay, so inverse of a 2 by 2 matrix. What do we end up with? Well, 1 over, what's our determinant? -1. And then, what happens? Swap the diagonals. So -1, 1. And then you make things negative. So -0, -2. Yes? We swapped our diagonals, and we made the off-diagonal terms negative. Do you think it should be a positive 0? Am I wrong? I mean, I'm not wrong. Remember, we still have to multiply through by this negative from the front. See, that negative will cancel with that negative. And so we'll end up with 1, 0, 2, minus 1. So it happens that it just works out very nicely in this particular case. Well, that's nice. That's nice. Okay, good. Well, now we can compute e to the at. So that's our cosine t, 2 cosine t plus sine t, sine t minus cosine t plus 2 sine t times 1, 0, 2, minus 1. Okay. Well, we get cosine t plus 2 sine t, right? Because we multiply cosine t, 2 sine t. Okay, how about this next entry? What do we see? Negative sine t. All right. Now, how about, this is the tough one. Let's say we'll have a 2 cosine t, but then we're going to subtract 2 cosine t, so the cosine t's cancel. Then we have a sine t plus a 2 sine t. Oh, sorry, 4 sine t, right? 2 times 2. So that would be 5 sine t. And our last entry. Oh, that's good. 0, and then just flip the signs. Cosine t minus 2 sine t. Okay. Nice. Now, and this is true. It actually works. And you might be thinking like, Steve, that's remarkably close to the matrix you started out with, isn't it? Your 2, minus 1, 5, minus 2 coefficients. Well, there's a little bit going on, but try not to overthink it, because it's probably better just to do the process than try to say, let me nail the pattern down. It's hard to memorize these patterns. Are we done? No, we found that piece. We still have to do all that. Okay, so don't worry, we have more paper. I know you were worried about that. Okay, let's talk about e to the minus at, because that's something else we're going to need. Now, the nice thing is, how do you go from e to the positive at to e to the negative at? What do you think you do? Well, take the inverse of the matrix is a bold move. I would probably discourage you from trying to do that. Another way to think about this is EA minus T. So what does that mean? That means that everywhere where you see a T, you now put a negative T. So this would be cosine minus T plus 2 sine minus T minus sine minus T 5 sine minus T cosine minus T minus 2 sine of minus T. And then we start saying, but we know things about these functions. We've trained ourselves. For example, some people might say that sine is a very unusual function, a very strange function, a very weird function, perhaps an unusual function. And some might even say that sine is right. So sine of negative t, negative comes out. What happens with cosine of negative t? Basically the negative doesn't matter. It's what we call an even function. So this is cosine of t minus 2 sine of t, sine of t, negative 5 sine of t, cosine of t, plus 2 sine of t. All right, so we have our pieces, because we know what f is, we know what e to the minus at is, and we know what e to the at is, so we're ready to get to work. Okay, so let's start with just doing e to the minus at f of t. So we're taking what we just did, cosine t minus 2 sine t minus 5 sine of t, sine t cosine t plus 2 sine t times 0 secant t. Okay, well, what do we get? We get, in the top entry, the first entry we have tangent. People were quick to jump to it. So it's sine times secant, and then people were like, hey, that is really tangent. Hey, nice. And the reason that we say tangent is nice, it's on our list. Okay, that's the top entry. What's the bottom entry going to be? Well, I'll start writing some things down. Cosine t secant t plus 2 sine t secant t. Does that simplify to a nice expression? 1 plus 2 tangent. Oops, looks like I wrote a t there. Let me try that again. 1 plus 2 tangent t. All right. Good. So, now, what's next? Yeah, we've now got the inside part, so we're now going to integrate e to the minus a t f of t dt, which is the integral of tangent t, 1 plus 2 tangent t, Do we know what the integral of tangent is? It is, on the formula sheet, natural log secant is correct. How about the integral of 1 plus 2 tangent t? Do we know that? T plus 2 natural log secant t. What haven't we put down yet? Plus c. And now, just to help emphasize what's going on, c is a number, so I'm going to write this as cd. Just as it's essentially, you can pull out, you get a constant for each entry, so you have a constant vector. If we were after our particular solution, we just say, don't worry about that, worry about this. But if we're after a general solution, we throw it in. Okay, are we done? No. Just when you thought there was a ray of hope. No, there's a ray of hope. What's left? Got that e to the at in the front. Okay, so I hope you took notes so you remember what e to the at is. But we are close. We're rounding that corner. So we have x is e to the at integral e to the minus at f of t dt, which is e to the at is cosine t plus 2 sine t, and then 5 sine t below that, and then minus sine t, and cosine t minus 2 sine t. And then we have our log secant, our t plus 2 log secant, plus, I'm out of space, our vector cd. Okay, I ran out of space on the edge. And so we multiply our last thing. So let's multiply our matrix times our vector here. And so, not really much to say, you just sort of patiently work through it. You have cosine t plus 2 sine t log of secant t minus, then you have sine t times t plus 2 log of secant t. We'll come to the other part in a minute. And then we have bottom 5 sine t log secant t. And then plus cosine t minus 2 sine t times t plus 2 log secant t. Plus other stuff. We'll come back to that in a second. Does any of this simplify? So you're going to do some distributing here. And if you look upstairs, you'll see there's a 2 sine, well, if it was legible, there's a 2 sine t log secant t and a minus 2 log secant t sine t. So those actually end up canceling. So what you end up with on the top is cosine t log of secant t and minus t sine t. And that's what the top simplifies to. All right, well, what about the bottom part? I have bad news. It's going to be a lot here. Well, we can FOIL, right? So just do all possible ways. You have a 5 sine t log secant t, and here you have a minus 2 sine t, a plus 2 log secant t, so that's a minus 4 sine log secant. So if you can take this 5 and that minus 4, you get a single sine t log secant t. Then you can get a plus 2 cosine t log secant t. And then we get a minus 2t sine t. So that part here, that's your particular solution. Okay. Yes? Did I make a mistake?
T cosine t.
Where did I forget a t cosine t? Ah. Plus t cosine t. That's where I forgot it. Yes. Thank you. Whew. It felt too easy. What else do we need? Well, we need, what happens? Well, this vector of constants, when you multiply by this e to the at, it actually says, oh, it's like taking that constant c times your first column, cosine t plus 2 sine t, 5 sine t, and plus d times your second column, minus sine t, cosine t minus 2 sine t. And this part is your xc. All right. Phew. Good. Done. No, not class. Class isn't done yet. We have 10 minutes. Good. Now it's your turn. Or we can skip your turn and do a brine problem. So many choices. So many choices. We should probably practice. Okay. All right. We've had so much brine. All right. Well, the next problem says use variation of parameters to find the general solution. X prime equals minus 2, 2, 2, 1, x plus 3e to the t, 5e to the t. Is this a problem that you could do by undetermined coefficients? Yes. Is this a problem that you should do by undetermined coefficients? It is. Are we going to do it that way? No. That's right, because we're going to follow the instructions. Because people who read, lead. Wait, I don't know if that's a real thing. But, you know, it helps to read. Maybe we can compare. Okay, how about e to the at? I have 1/5, 4e to the minus 3t plus e to the 2t, minus 2e to the minus 3t plus 2e to the 2t, minus 2e to the minus 3t plus 2e to the 2t, e to the minus 3t plus 4e to the 2t. Is that what you got? Okay. Maybe. When you put in e to the minus at, essentially you just have to flip all the signs in the exponents. Then you carry out the computation for e to the minus at, e to the t35. You integrate, and then you just have to multiply the original e to the at times the result and simplify. What could be easier? But unfortunately, we're out of time. So, all right. Moral of the story? Undetermined coefficients.